So as we get started, what I'm going to have you do is I'm going to have you looking at the first page of the notes. I want you just to try that first page. The first page is mostly a review of exponentials, so it should feel really familiar. So I want you to go ahead and pause the video and give these first two examples on the first page a try. So we have this first one if you need to pause and work out the first one. And then this is our second example that I want you to try. So go ahead and pause the video and give those a try. All right, so hopefully you had a chance to give those a try. This is what we should have gotten for this first example. So remember, we're just given those x values and you're just plugging in those x values to this function and figuring out what those y values would be. So that graph is the one in blue. So the domain of that's an exponential graph. So the domain is negative infinity to infinity. The range is 0 to infinity. That x-intercept is at, or that y-intercept, excuse me, is at 0, 1. And then that horizontal asymptote is at y equals 0. So now when we found the inverse, meaning we just switched x and y, all we did was take this table and flip it over here and make all of the x's y's and all the y's x's. What you should also notice is that also flipped your domain. So my domain is negative infinity to infinity here, but now that's become the range here. And the same thing for the range became the domain. That's important to note because as we start to solve and evaluate logarithms, we're going to notice that this domain being 0 to infinity is going to affect a lot of the problems that we solve and what numbers can be negative or positive. I also want to point out that in your exponential graph, you had a y-intercept of 0, 1. In your logarithm graph, this is a logarithm graph. We haven't quite gotten to how to graph that, but that's what that is. There is no y-intercept because it's not going to cross that y-axis because we actually have a vertical asymptote now at x equals 0. So we don't have a y-intercept, but we do have an x-intercept at 1, 0, which would make sense because all we did was flip that ordered pair. So if you haven't got a chance to try the second example, go ahead and pause this video again so that you can try that example on your own. If you have, let's go ahead and look at those answers. So a lot of the information in terms of the graph is similar on our identifying domain and range. But again, all we did was plug in to this exponential function to get our table, and then to find the inverse function, which is our logarithm, we just flipped x and y. So our exponential graph is in blue, our logarithmic graph is in red. And then remember, our domain and our range had flipped here because of its inverse. Now, the important thing to realize is that when we find the inverse, we're reflecting. The reason that this graph looks funny is that we reflect over y equals x. We reflect over this line here. Sorry, it's a really thick line on my board. But we're reflecting, so see how this blue part matches this red part? And then the blue part on the left matches the red part on the right over here. So this is a reflection over that line. So that little graphing activity leads us into the second page of our notes, which is telling us that the inverse of an exponential function is called a logarithm. So that red graph that was in those first part of that video is our logarithm graph. And so today we're really just going to talk about how we can write an exponential in logarithm form and a logarithm in exponential form. Because they're inverses, you can write them both ways. So if you see here, it says the inverse function of the first example, so this was that first thing that we graphed, is written as log base 2 of y equals x. And then for that second example, we have y equals 1/2 x. So then we would write that as log base 1/2 of y equals x. So it's very simple to rewrite them. So if we look at these examples down here, and what I want you to notice is that a log is equal to its exponent. So this value, the value that we have right here, and sometimes that's the value we're going to solve for, is the exponent of the original, well, of an exponent problem. So if you are looking at this exponent here, that's the answer. The x is the answer to your log. So let's try rewriting them. So looking at our first example, we have 2 to the third power equals 8. So this is an exponential form, and we want to write it in logarithm form. So we're going to change this to log, And then if you think this is 2 to the third power, this base is 2, my log is going to have the same base. So it's going to be log base 2, and then it's going to be of 8 equals 3. Because remember, your exponent is what is your log is equal to. So then we're going to do this one. 5 to the 0 power equals 1 would be log. Our base stays the same. So the 5 was our base. The 5 is our base of 1 equals our exponent, which is 0. All right, so then let's try going the other way. So I have log base 7 of 49 equals 2. So again, your base is 7, so that stays 7. And then your answer is the exponent, so that's the second power, equals 49. Another way people like to look at it, and when they rewrite, is they kind of make a circle around the equal sign. So if I start at my base, I go 16, and I'm making a circle around the equal sign to the 1/2 power equals 4. And all of these statements are true. So if you kind of solve this in your head, so I have 7 to the second power equals 49, that's true. 16 to the 1/2 equals 4, that's true. You would never want to write something that wouldn't give you a true statement. So for instance, let's say you're rewriting and you wrote it as 7 to the 49th power equals 2. Well, you know that's not true. So something in our rewriting must have gone incorrectly. So keep that in mind. So what I want you to do now is I want you to go ahead and pause this video, and I want you to try these problems here, this table. So if it's an exponential form, I want you to rewrite it as a log. If it's in log form, I want you to rewrite it as an exponential. So go ahead and practice that now. So this is what we should have gotten when we did our rewrites. So 2 to the 5th equals 32 is log base 2 of 32 equals 5. 3 to the negative 3 equals 1 over 27 would give me log base 3 of 1 over 27 equals negative 3. And so on and so forth. So if you're struggling with this, yeah, hopefully with these examples you can kind of see the pattern that we're creating. If not, remember that there are office hours tomorrow that you can stop by and ask questions and we can talk about. But really, this is just a pattern. They're all written the same way. So we're always taking the base, writing it as the base. What it equals is always the exponent of our log, and then it equals that big number right there. So keep that in mind. This is just a pattern that we're following. This is not, each problem does not have a different form. So hopefully by the end of these examples, you kind of saw the pattern. So now I want to just look at this challenge question. Rewriting should be something that feels pretty easy and familiar to us, or as you went on, it felt pretty simple to do. But there is different ways that they can ask the question. So for instance, this challenge question says, find B to make the following two equations equivalent. So as you can see, this first equation is an exponential form. The second equation is logarithm form. So what they want is that these two have the same values that you're solving for. So what I would do is I would either take the log form or the exponential form and write one as the other. So let's say we take the exponential form and we write it as a log. So that would mean we'd have log base 5 of 7 equals x minus 1, right? Because 5 is our base, x minus 1 is our exponent, so that's what it equals. So this would be the log form of this exponential. So as you can see, it matches this. It's just kind of written backwards. So if I rewrite this, and I just flip the side of the equal sign, so I have log base a of b equals x minus 1. All they want to know is what are the values of a and b that make these two the same. So that would mean a would need to be 5 and b would need to be 7. And in this case, they're just asking us to find b, so b is 7. So hopefully that makes a little more sense. It's really just a rewrite question, just worded a little differently. So then the next thing we're going to move on to is evaluating logs. So if I'm looking at this first example here, I want to know what this log equals to. What is the value of this log? So there's a value here that I'm trying to find. So in order to do that, I make the value x first so that I can figure out what that value needs to be. So now that I have it written in logarithm form, I'm actually going to rewrite it into exponential form. So I'm going to write it as 6 to the x power equals 36, right? That's the exponential version of this log. So now in order to solve, we want these two bases to be the same. So 36 is 6 to what power? So 6 to some power gives me 36. Hopefully you know that it's 6 to the second power. So now that these bases, these bottom numbers are the same, that means that the exponents are equal to each other. So this would tell me that x equals 2. So the value of this log, so log base 6 of 36 equals 2. My answer here would be 2 because 6 to the second power gives me 36. Good. Let's try another one. So if I look at number 2, again, I think it's easier if I write it equal to x first so that I can write it in exponential form. So I set it equal to x. So now I'm going to write it in my exponential form, which would give me 4 to the x power equals negative 64. Now, I want to find some base. 4 to what power gives me negative 64? And here's where we lie in the problem. Can you think of an exponent that is going to change 4 from a positive number to a negative number? And there's not. There is not one that would turn 4, right? If no matter what this number is up here, if it was a positive number, you would get a positive number. If it was a negative number, remember from our exponents, this would not give me a negative answer. This would give me 1 over 16. So even a negative exponent does not give me a negative number here. And that plays into, remember we were talking about that domain and how domain only went from 0 to infinity? That's because these values can't be a negative number. So in this case, this would be no solution. All right, so let's try the next one. So the next one tells me log base 9 of 1, and we're going to set that equal to x. So I have 9 to the x power equals 1. Well, remember, we want our bases to be the same. So I want 9 to the x power to equal 9 to some power. Well, there's only one power that makes a number 1, and that would be 0, right? Anything to the 0 power equals 1. So 9 to the 0 power gives me this 1 here. So that means that x needs to equal 0, right? When my bases are the same, my exponents are equal to each other. So we just set x equal to 0. So that means that my log, when I evaluate, log base 9 of 1 equals 0. And if you want to check that and rewrite it, is 9 to the 0 power equal 1? And that's true. So then we know that we found the right answer, that our answer here would be 0. So go ahead and pause the video and try 4, 5, and 6 while I clean this up so that we can go over those ones together. All right, now that my board is cleaned up a little bit, let's finish these last 3 problems. So again, when I want to evaluate a log, I'm going to set it equal to x. That way I can rewrite it in my exponential form. So I would have 2 to the x power equals 32. So again, I want to be able to solve this. I want my bases to be the same. So if I have 2 over here, I need this to be 2 to some power. So 2 to what power would give me 32? And that would be 5. 2 to the 5th power. 2 times 2 times 2 times 2 times 2 is 32. So 2 to the 5th equals 32. So now that my bases are the same, I look at these exponents as the same as well, or equal as well. So that means that x value would equal 5. So log base 2 of 32 is equal to 5. So my answer here is 5. All right, let's try the next one. So if I set this equal to x, I have 3 to the x power equals 27 when I rewrite that into exponential form. So then again, I need my bases to be the same. So this base is 3. So then I want this base to be 3. So 3 to what power gives me 27? That would be 3 to the 3rd power. So now that my bases are the same, my exponents are equal. So that gives me x equals 3, which means that log base 3 of 27 equals 3, which we know is true because if we tried to write this in exponential form, 3 to the 3rd power gives me 27. Now, one thing I haven't touched on yet, but was at the top of page 2, is if there's no base written here, it's an assumed 10. So this is going to be a base of 10. Logarithms are always out of a base of 10 unless we write a number here. So this is going to be 10 equals x. So we have 10 to the x power equals 10. So in this case, my bases are actually the same already. And this would be a 10 to the first power, right? Any number is the first power. So my bases were already the same, so my exponent will be 1. So then log base 10 of 10 equals 1. All right, so hopefully you feel comfortable with rewriting and evaluating. That is what the practice on Schoology is all about. So if you go ahead and print that, or just on your line sheet of paper, keep practicing. And then if you have any questions, remember there is a link in Schoology so that tomorrow you can join my Zoom and ask me any questions that you have. So please, please, please come in. Even if you don't have any questions and you just want to say hi, I'd love to see you again and talk to you again. But if you have any questions, make sure you come by because there's a quiz on this stuff on Friday. So you want to make sure that you've got this down. So I hope this was a good first lesson. And please let me know if you guys have any questions.